Okay, it's on. All right, here's our new problem for today. This one is not bad. It's not bad, but we've covered stuff from Unit 1 last year. We've covered stuff from Unit 2, and we covered forces, and we covered work energy theorem. So there's our first 4 units. And I did one on centripetal force. So there's Unit 6. But I skipped that unit on momentum. Now we have to introduce momentum stuff, okay? So notice I'm launching the electron. The electron's moving to the left at 3 × 10⁶ meters per second. Sorry it's written so small. I kind of got all these numbers in there and I couldn't cram them in there any closer, so I forgot to put the velocity initially. All right, the electron's moving to the left 3 × 10⁶ meters per second. And it's positioned directly in between the 2 plates. Okay, and the plates are separated by 2 centimeters. Okay, so we got a separation distance. The length of the plates is 4 centimeters, and we have a potential difference of 60 volts. All right, now, what's different about this problem than the one I did on Friday, I had the plates this way, and I accelerated the proton, I think, on Friday across the plates, right? We started at rest and we accelerated. I've already got this one moving. This is more, the next step to this is I put a perpendicular magnetic field in here. This is more like what the particle accelerators do. Okay, so if we can take a field trip over to CERN, over to Switzerland, we'll get to experience it. Okay. So, first thing, how will I ever determine the electric field between these plates? What's the equation for electric field? Parallel plates, folks. Okay, that's pretty darn simple, right? I told you parallel plates are a piece of cake. Okay. Yeah. Don't forget. 3,000 volts per meter. Direction. Field line's positive and negative, right? So my electric field is going that way. Everyone agree with that? That's piece of cake. Okay. All right. We'll know the force on the electron. What's the equation for the electric force? Force equals EQ, right? Okay, fine. Easy enough. Will I ever use the KQQ over R squared for parallel plates? No. No. Never use any of those KQ over R equations when we're dealing with parallel plates, right? Why not? What's the big difference between parallel plates and point charges?
The plate is a point.
Point charges radiate in 3 dimensions, right? So the field is the same no matter where I measure it in between a parallel plate, right? Field right here, 3,000 volts per meter at 270. Field right here, 3,000 volts per meter at 270. Doesn't matter how far I'm away from the positive plate, the field stays the same. So the force is always constant, right? Okay, so EQ, 3,000 volts per meter times, I need the mass of the electron, right? I keep trying to mess you guys with that one because you don't keep using that. What's charge? Thank you. Okay, easy. 4.8 times 10 to the negative 6 newtons. What's my directional component? Oh, bad, Bryce. Holy cow. Shame on you. Yeah. Great. Now you're permanently on the internet. I just called you out permanently on it. guess I can't use your last name. So, all right. Force is up. Let me turn my laptop around and do a screen capture. Lay the price right here. So, all right. What will be the magnitude of the acceleration in the x direction? There's no force.
Very high.
I like that question. Right? There's no force in the x direction. The force is in the y direction. Hey.
Greater unit.
I'm on air. I gotta watch this. This is going over real well. Let me tell you. I might as well just go ahead and hit the stop button now. Starting to look like a projectile motion type problem, isn't it? Launched horizontally, the only force is in the y direction, so we're going to have a similar type of path, right? So, once again, you got to break out that topic too, right? So we got to add the projectile type problem. Okay, acceleration in the y direction. This will be hard. Force divided by mass, right? Okay, so force divided by mass. All right, so I have my 4.8 times 10 to the negative 16th newtons divided by what's the mass of the electron? 9.11 times 10 to the negative 31st kilograms. Okay. Should be a pretty small acceleration. It is 5.27 10 to the 14 meters per second squared. There's your unit. Are you happy now?
Thank you.
All right. Here's the next question. I want to know how much time before the electron collides with the plate. Kinematics, that's right. I've got acceleration. I know V initial. What's V initial I need to use?
3 times 10 to the 6.
No.
You need to use V initial y.
0.
V initial in the y direction is 0. That's the V initial, that's the x velocity, right? It's like a projectile, folks. It's not, just like a horizontal projectile. V initial in the y direction is 0. See, the time wouldn't matter if I just held this electron right here and just let it go. It's going to accelerate that way. It's still going to collide with the plate the same amount of time.
Good.
Just like if I add a ball and I drop it versus throwing one horizontally. They're both going to hit the ground at the same time, right? Same type of problem. Okay, so I know V initial 0. I know my acceleration. I'm solving for time. And I know the displacement that's going to go, which is 1 centimeter, right? In the y direction. So, delta y is V initial times t plus 1/2 at squared rid of that. So time is square root of 2y over a. All right, so 2 times 0.01, what do I got? 2 centimeters there. My acceleration 5.27. Everyone with me so far on how I set that up? Everyone understand why I used the 0.01 meters? Because I said this is right in between, right? So it's only going 1 centimeter. Should take a while, a couple of days probably, 6.16. So 0.16 times 10 to the negative 9 seconds. Get your stopwatch down, right? Get your electron catcher up here. Someone else holding the stopwatch. Oh, I want to know where it collides at on the plate.
On the bottom.
Yeah, it's going to hit the bottom plate, right? Delta X, just like on the projectile, folks. If I want delta X, I need to use V of X. And since V of X is constant, V equals X over T, right? Delta X equals V of X times T. Times 10⁶ meters per second. Times 10⁶ times 10⁻⁹. And 0.85 centimeter marks. We're just going to collide with that plate. So let's sketch the path that this thing's going to travel then. Some upside down projectile, right? Now, it's gonna, don't do this, folks. You will get point taken off if you try to sketch it and do this. Okay? That is bad. The second it gets between the plate, it's going to experience the force. So I want to be able to, obviously the 1.85 marks approximately here. So I'm going to curve that immediately towards that, just like a projectile would be. But this is an electron.
Oh,
this is my negative plate. And force is at 90 fields of 270. One more to go. What's the change in momentum in the X direction going to be? There is none. Right? I don't even need to mess with the X direction to this. And my change in momentum direction is already established. It's up. There is no change in momentum to the right. Now, I could solve for the momentum in the X, momentum in the Y. We could solve for the actual momentum. I just asked for the change in the momentum. So the change in momentum is simply straight up. All right. Equation for momentum. Mass times velocity, right? And change in momentum is m times v final minus v initial. Okay, so let's do it that way. Initial y is 0. V final, I'm going to have to break out another kinematics equation here. Would you agree with that? V final equals v initial plus at, so I'll just sub that in. So change in momentum, 9.11 times 10 to the 31st times A, which is 5.27 times 10 to the 14th. Times time, 6.96. Good there? Everyone understand what I did with that? Once again, momentum's mv, so change in momentum is m times v final minus v initial. And the v initial in the y direction is 0. Okay, 2.96 times 10 to the negative 24. Unit for momentum. There's no set units to this. Remember, it's not like a joule or a newton. It's basically what you have. It's a kilogram meter per second. Okay. kilogram meter per second at 90 degrees vector. Hang on, I'm not done yet. Most forgotten variation of Newton's second law. What's another equation for changing momentum?
What's that?
Impulse equals a change in momentum, right? All I have to do is take my 4.8 times 10 to the negative 16. Actually, yeah, times the time. But look at this. Right? This is A, isn't it? When I just subbed that in, I already did it. I just had to redid a calculation. I didn't even need to. So you can have a shortcut right there. All you need is force times time. Everyone okay with that? I don't think that even shows up for till the end of the week or so. So I mean, I'm ahead of the game practice problems. And I actually kind of like doing this because I'm doing the practice problems and then they show up on a later worksheet. That's kind of forcing you to go back and think about them a little bit, you know. But you got them, okay? All right.